Yeah, so as I said in my abstract, there seemed to be a sort of surprisingly high density of really remarkable results in combinatorics proved in the last few years. And I thought the best thing I could do on an occasion like this with a mathematically diverse audience would be just to give a very sort of superficial talk in which I'll just describe as best I can actually 6 major results that have been proved fairly recently, just to give some idea of the how I chose these things. I'm not trying to claim that they're the most important results in the last 5 years. So if your result is not mentioned, you shouldn't feel offended. I'm judging that it wasn't as good as these 6 results or anything like that. There's a sort of quanta test, which I like quanta, but I think it should be regarded very definitely as a sort of more of a necessary condition than a sufficient condition for inclusion. So it's just a sign that even necessary. There's some discussion about that, but in combinatorics, I think there's a sort of, if you reach a certain degree of notability, then it's quite likely that it'll get reported in quanta sets. So it sort of correlates reasonably well with the sort of the real criterion. I've had a very rigorous cutoff of 5 years, which actually resulted in cutting off some quite notable results proved just over 5 years ago, about a matter of months. And most importantly, I just solved a problem that a lot of people had thought about and wanted to solve and weren't sure that it, in my case, I could say, I'm old enough to say, wasn't confident that it would be done in my lifetime. I just want to mention in parentheses, although it's slightly embarrassing to mention this, I was very fortunate to be a co-author with 3 other very formidable authors who were Ben Green, Freddie Manners, and Terence Tao on a result that did make it into quanta. I'm only saying that not to sort of boast, but just to sort of pay tribute to my co-authors. I think what they did was absolutely remarkable. But I don't want to talk, it seems a bit weird would be strange to blow my own trumpet. But I would just want to give a quick shout out to those 3, but I'm not going to talk about that result. I did, in fact, talk about it on Monday this week. And then the last condition here, proved by new entrants. This was not an actual condition, it's just a sort of thing that turned out to be the case with a lot of these results. They weren't sort of proved by the usual suspects, or maybe you could say in some cases they were usual suspects, but they'd become usual suspects very rapidly. So a lot of the people who prove these things are extremely young and in an early stage of their careers, just either PhD students or just out of a PhD. And that's another sort of thing that contributes to this excitement in the area. We've got this feeling that there's a whole extraordinarily talented generation coming up, so who knows what's going to happen over the next 10 or 20 years. Right, so since I'm doing 6 results, got only an hour, I've already wasted more time than I should have. So let me jump straight to my first result on the list. So probably most people in the room, even not just the combinatorialists, are aware of Ramsey's theorem, which says there are 2 ways you can say it. One is if you've got a graph with sufficiently many vertices, then you can find k of those vertices that are all joined to each other, or k that are not joined to each other. And then the other way we say it is if you take all possible edges, or take all edges of the complete graph with n vertices and color them red or blue, you can find k vertices that are all joined by red edges, or k vertices that are all joined by blue edges. And that's a theorem of Ramsey, so it's called Ramsey's theorem. Oh, I've put a sort of off-diagonal version. You can go for k vertices that are all joined by red, or L vertices that are all joined by blue. So it's a slightly more general thing, but it all comes out of the same argument. Let me just very quickly sketch what that argument is. You can either read what's on the board, or I'll just draw a little picture of a proof. So you've got a graph. Let's go with the coloring versions, because I've got these colored pens. So I'll just describe you a little algorithm that will give you a subgraph where the color of an edge depends only on the first vertex. So I take some ordering on the vertices. So I'll just pick the first vertex, and either at least half its neighbors will be joined by blue edges or half by red edges. And so let's suppose it's blue. So I had n vertices to start with, now I've got n over 2 vertices at least in here. And now I just pick the sort of smallest vertex in my ordering in this set. And it's, half of those are joined by red or half by blue. Perhaps it's red this time. Could be blue. And you just keep going with that process. You get smaller and smaller sets. And when you've done that, you can obviously go for log to the base 2n steps. You then have a bunch of vertices, and each one is joined to all subsequent vertices either by blue edges or by red edges. And once you've done that, there's one final step. You just apply pigeonhole principle again and say, well, half the vertices will be joined to all subsequent ones by blue, or half will be joined by all subsequent ones by red. So pick whichever of those is the case, and then you've got log to the base 2n divided by 2 vertices that are all joined by edges of the same color. So that's a simple argument that shows that the Ramsey number RKK, the smallest number n, if I invert the function log to the base 2n over 2, I get the function k goes to 4 to the k. If you do this a bit more carefully, as Erdős and Szekeres did, you can do a nice inductive argument. I won't say it, but you can quite easily improve that to this binomial coefficient, which is better than 4 to the k by a factor of 1 over root k. In the other direction, there was an extremely influential, sort of almost one-line proof of Erdős that gives a lower bound of 2 to the k over 2. And all you have to say is just color the edge. If you want to get a big graph, a graph with lots of vertices without any large cliques or independent sets, then, or let's say I'll stick with the coloring version. So you want to color your graph without any large blue cliques or large red cliques. Just choose your coloring completely at random. Work out the expected number of monochromatic cliques. You do a little calculation on the back of an envelope, and you find that the bound that comes out, it's really not hard, is roughly 2 to the k over 2. If you're very careful about it, you can do slightly better than 2 to the k over 2, but you get this. And, well, there's quite a big gap between, there's an exponential sized gap. This pointer seems not to be doing anything, but there's an exponential sized gap between this 4 to the k and 2 to the k over 2. And so it became very tempting to try to close that gap, because we have these two really quite straightforward arguments, one that gives the 4 to the k, one that gives the 2 to the k over 2. And you could ask a sort of ambitious question. You could say, well, let's look at the limit as k tends to infinity of rkk raised to the power 1 over k. Is it 4? Is it root 2? Is it something in between? In fact, does it even exist? So if you had some kind of submultiplicativity property or supermultiplicativity property, then you'd have some abstract argument that at least there was a limit. But we don't have such an argument, so it is actually still an unsolved problem whether it tends to the limit. For all we know, it could sort of oscillate forever and ever. That's actually, that's almost one of my favorite problems, because I feel it sort of tempts one to try to find some incredibly general abstract principle that sort of shows that in any problem like this, it must tend to a limit. But no one's come up with such a, it just lives in, that's absolute fantasy land at the moment. I don't think anyone has the slightest idea how to come up with something like that. So there's been quite a bit of progress on the problem over the years, but I think Rödel was the first person to get a small improvement on this 4 to the k over root k. Andrew Thomason have a very influential proof that introduced the notion of a quasi-random graph, which then later got taken up in a big way. Very roughly, the idea there is that in this argument here, if it's going to be tight, then sort of always when you pick a vertex, roughly half its neighbors will be blue or half its neighbors will be red, because otherwise you'll get a bit of an extra edge. I mean, an extra gain. You won't have to drop down to half the vertices. And more generally, if you pick, say, a couple of vertices and look at their joint neighborhoods, then you'll get a bit of a gain if neighborhood intersections are not roughly what you expect. And the more you sort of do this, the more you realize it's sort of pushing the graph to look somewhat random. But if a graph is completely random, then you don't have to do this extra annoying pigeonhole step at the end. You could just sort of just pick blue every single time and you'd always drop down by a half. In fact, now that I've said that, I've tried many times. It's a hopeless thing to do. You sort of think, surely you could just go away and sort of decide carefully whether you're going to choose blue or red in some way. And those sort of, it's very difficult to make anything like that work. But the sort of idea of that if it's tight, it forces it to be quasi-random and then you can do something else, has been used to make very small gains. So the state of the art until recently was, well, it was mainly due to David Conham, but it was sort of sharpened up by Ashwin Shah, who got the first bound that gave a super polynomial improvement on the root k. But none of this changed the fact that we couldn't improve on the 4 and we couldn't improve on the root 2 until March last year, when these 4 authors, Marcelo Campos, Simon Griffiths, Robert Morris, and Julian Saras-Raboude, proved the upper bound that I've stated. I'm not absolutely sure whether that's the most recent thing, but then they proved an upper bound that, if you do the calculations, works out at about 3.95 to the k. So even 3.99999 to the k would have been incredibly exciting. Now we've got down to, so we've got the first exponential improvement to the upper bound. The lower bound is still root 2, and then there was a very interesting talk by Jacques Verstraete a couple of days ago at this conference, which sort of indicated, I think, that he believes that probably the lower bound can also be improved. I'm not sure if I'm representing him correctly there when I say that, but if that's the case, then I suppose the most natural bound would be 2, but not for any particular reason. One interesting fact about the proof, before I move on to the next result, is that it didn't actually use quasi-randomness. It somehow went back to an elementary approach. Although I slightly dismissed the sort of elementary approach, in a way it's a sort of just a much more sophisticated elementary approach than the kind of idea that I was indicating. That was a bit of a surprise, actually. And it used this concept of a book that had come up already in the field. But I must move on and say that actually I had this impulse, and I'm sure many other people did as well, that RKK was such a hard problem, then why not look at a problem that ought to be easier, which is looking at RKL, where k is fixed and L tends to infinity. So let's just have a quick think about that. So if you just do the same sorts of arguments that I sketched for RKK, then the bounds you get out for R3k, so now we want to have, say, a red triangle or a blue set of k vertices that are all joined to each other. Or similarly, R4k would be 4 vertices that are joined by red edges, or k that are joined by blue edges. You get these bounds here. So roughly k squared for R3k, and between, so in other words, both the probabilistic lower bound and the sort of easy upper bound give you roughly k squared for R3k. For R4k, the probabilistic lower bound actually is a little bit more difficult than the one for RKK, funnily enough, but not that much harder, but it's just a slightly harder thing. Gives you k to the 5 over 2 and k cubed. So over the years, R3k was tightened up until actually now the best known upper and lower bounds differ just by a constant factor. So that's sort of almost problem solved. And even the difference in the constant is now quite small. But R4k was somehow one of those problems that makes you think, well, a gap of square root k, such a big gap, it must be possible just to think hard enough until you solve it. So I actually will admit to having spent a lot of time on R4k in the past. In retrospect, I now know why I was sort of wasting my time, because I'm always optimistic, so I really thought it would be possible to improve the upper bound. And, well, it turns out you can't improve the upper bound. So the very interesting aspect of this proof it really is the case that if you just use a random graph, you're not going to do better than r than k to the 5 over 2. It's a slightly dangerous thing to say, but oh, by the way, I should just make the general remark that several of the results I mentioned will have at least some of their provers in the audience, and I apologize if I just say some nonsense or misrepresent. It's funny to talk about things that the people know much more about than I do. But anyway, you somehow have to do better than randomness. You want to have a graph that's sort of incredibly nice in the way that a random graph is nice, but to do even better than that. And one way of doing that in some circumstances, like when you're looking for, I won't say what these are, but Ramanujan graphs, for example, is to use algebraic structures that are sort of so nice that the kinds of things that you get from random constructions happen, but sort of really very exactly. Here it seems that you can't just sort of pick your favorite algebraically constructed graph and show that it's an example. It's a sort of interesting hybrid of random methods and algebraic methods. So you have these algebraic constructions from which you randomly sample, but because you started with this really nice algebraic thing, it sort of gives you graphs that are better than if you'd just chosen a purely random construction. And that's been a bit of a theme, actually, in combinatorics recently. There are quite a lot of advances. There was also an advance on the lower bound for the Ramsey numbers, but where you have 3 colors instead of 2, proved by that sort of method. The only reason I'm not mentioning the authors is I can remember one of them, but he wasn't anyone. But David, if you're here, maybe you can tell me who your co-authors were. I'm sorry.
Asaf Ferber.
Okay, Asaf Ferber, that's right. Yes. Okay, so but I've now spent too long on that, so I'm going to move on to the next thing. So here's a theorem that's very well known to all the combinatorists in the audience and been very sort of close to my heart for a long time, Samouredis' theorem, which says that if you take any delta and any k, you can find an n such that any subset of the numbers from 1 to n of size at least delta n contains an arithmetic progression of length k. If you've not seen that before, then it's not obvious that it's sort of obviously quite a sort of pretty question, but it's not obvious that it's not something that's just an easy exercise or false or whatever. But it turns out to be true and very far from an easy exercise. And there's a lot of sort of quite famous work on this. And so the first proof just for k equals 3, k equals 2 obviously is totally trivial, but k equals 3 was done by Roth in 1953. In our field, when we say Roth's theorem, we usually mean this, and not his theorem on Diophantine approximation. And he got a bound of constant over log n for the density that you need in order to guarantee an arithmetic progression of length 3 in a subset of 1 up to n. And there are all sorts of reasons that the case k equals 3 is easier, which I won't go into. But I just want to draw attention to the fact that so there was a whole sequence of results there have been particularly in the last sort of 20 years, but that have been improving this log-log bound. But all of those were improving 1 over log-log to 1 over some power of log, and trying to get this power of log to be better and better. So it started off with something like 1 over 20, and in a sequence of steps, it got to, eventually, it got to what we see here, sort of 1 over log n to within log-log factors. In fact, the first person who got to that stage was Tom Sanders in a remarkable breakthrough. I don't know how many years ago, but 10 to 15 years ago. But that was tantalizingly close to what came to be known as a logarithmic barrier, because if you go beyond the logarithmic barrier and get something just slightly better than log n, or even just 1 over log n itself, or in fact, if you're really careful, even just a tiny bit bigger than 1 over log n would suffice, you would be able to prove that the primes contain infinitely many arithmetic progressions of length 3, which is actually a known result since the early 20th century, but without using anything but the primes other than, say, Chebyshev's theorem, just using that they're reasonably dense, sort of, because you'd have density 1 over log n roughly, and then if you could do so. And it would also prove the first case of a very famous conjecture of Erdős, that if you have a subset of the integers with the property that the sum of the reciprocals diverges, then it contains arbitrarily long arithmetic progression. So this would prove that it contained at least an arithmetic progression of length 3, which was unknown. And there's a big contrast between this and the lower bound, which is this e to the minus a constant root log n, which was done in 1946, and there have been some refinements of that, actually one of which we heard about again. It's always nice sort of this week, a very nice proof by Elsholtz, Hunter, Prosker, and Sauermann. Lisa Sauermann was one of the speakers who talked about it. Improving this constant by, just improving the constant c in there, which it had somehow the fact that that was quite a notable result is just reflects the fact that it had stood almost still. In particular, the constant had stood still since 1946. But so there was a big, actually, historically, this is that was very recent. But the previous constant was not at all recent. So we still had this enormous gap. And then suddenly, two things happened. So this just about makes the 5-year threshold. So Thomas Bloom and Olof Sisask finally beat the logarithmic barrier. So got the first case of Erdős's conjecture. And they did that by actually mixing some very nice some of the ideas that had gone into getting to log in the first place, with some ideas that I haven't got time to talk about, but some ideas of Bateman and Katz connected with the cap set problem, which would definitely have made it into an equivalent talk, say 10 years ago, or no, not 10 years ago, but sort of 7 years ago or something, but that's another story. And then, to everyone's amazement, early last year, and this was a real case of Thomas Bloom and Olof Sisask were sort of well known in the community, so to speak. Kelly and Mecca were not well known in the additive combinatorics community at all, because they're computer scientists. But they just sort of suddenly burst onto the scene with a bound that is not exactly the same as the Berend bound, but it's of the same sort of form. It's e to the power of log n, or e to the minus the power of log n. And that power is 1 over 11. So if it was 1 over 2, then we'd have something that was really close to the Berend bound. But it's definitely sort of totally different order of magnitude from what we had before. And even more interesting was that, not even more interesting, but sort of equally interesting was that the proof was surprisingly not that bad. And it also, there was a kind of a received wisdom about what proofs of this thing should look like, which it didn't exactly follow. So there were some surprises in the proof as well. So it was really a very nice breakthrough. As I'm now getting slightly worried that I'm not going through fast enough. So going back to Semirates' theorem, let me just give a very, very quick idea of some of the thinking behind at least one way of doing it. So you've got a subset of 1 to n. You think of 1 to n as the integers mod n instead of just the interval of. And you define this function, which you call the balanced function. So you identify A with its characteristic functions as a 1, 0 function, but it's more convenient for many purposes to look at functions that average 0. So you just subtract the average from everything, and so you get this balanced function. And then there's a relatively easy result that says that if you want to, there's a sort of general philosophy that random subsets contain roughly the number of arithmetic progressions that you would expect. So if you had to pick a random subset of 1 to n, then it'll contain the number of arithmetic progressions it'll contain will be roughly delta to the k times the number of arithmetic progressions in the whole of 1 to n. It doesn't make sense to talk about a random set, but we can try and have notions of quasi-random sets, so it's going back to quasi-randomness. And one way of measuring quasi-randomness is some objects called uniformity norms. And there's a result that says that if this function f is small in a certain norm, which I'll just say a little bit about in the next slide, then A must contain roughly the right number of arithmetic progressions of length k, where the right number means the number that a random set of the same density would contain. So what do these norms look like? Well, here's the U3 norm, and I think if you've seen the formula for that, you can generalize that, or you can sort of be confident that you would be able to generalize that. So what do we have here? We take the average over all x, a, b, and c, and then we look at all possible products where I take x and subtract some subset of a, b, and c from it, put in complex conjugates if I subtract an odd number of things. So you can then just generalize. And that gives you the 8th power of the U3 norm. You have to prove that that's a norm as well, but that can be done. Now, once you've done that, you have a sort of potential way of attacking Semmelradius theorem. So you take your set A and you say either it's quasi-random in this sense, which means that the function f has a small norm, in which case you're okay, you've got roughly the right number of arithmetic progressions of length k, or it's not quasi-random, in which case this function f has a large UK norm. And then you want to be able to say something about f that will enable you to finish the proof. You want f to have some kind of structural information that will enable you to go on and, well, what actually happens is it goes on, it'll enable you to find a sort of a large sub-progression where A is denser than it was in the original thing, and then you can sort of iterate that process, get denser and denser, A being denser and denser in intervals until you reach a contradiction, and then you've proved Semmelradius theorem. But you didn't need to follow what I just said. Just keep in mind that because of this first observation, we are very interested in what it says about a function if its UK norm is large. And so in a paper that I wrote about Semmelradius theorem, I proved this theorem here, which, well, actually it proves something a bit more. I've slightly oversimplified it, so but although this does follow from what I said, what you might call a weak inverse theorem. So it finds a certain degree of structure. What it says is that you can find some arithmetic progression p, reasonably long, inside which the function f correlates quite well with a polynomial phase function. So you have some polynomial phi, and you produce this expression here, e to the minus 2 pi I phi, well, e to the 2 pi I phi x over n. So you can think of that as just a sort of polynomial thing, but that's been exponentiated. And that correlates reasonably well with f. So by a sort of non-zero amount that depends only on c. And you can then use that to go on and get a proof of Semmelradius theorem. But for other purposes, which I'll come to in just a second, it's a bit of an unfortunate aspect of this that you have to pass to a sub-progression. So you get this correlation on a small sub-progression, but what I'd really like is to understand the structure of the whole of f and not just some little part of f. And just one indication of why that's complicated is that it turns out that if you look at the whole of f, you have to take into account functions that are a bit more general than just polynomials. And I've just given you one example of a sort of generalized polynomial, where what you do is you write everything in base root n, so to speak. So you then have two coordinates, and then you take something that depends quadratically on those two coordinates. And that doesn't have to be the same as something that just depends quadratically on n. So you have a sort of higher rank something that looks a bit like a quadratic form rather than just a straightforward quadratic polynomial. And things get more and more complicated as the degree gets higher. So Ben Green and Terence Tao, after proving the famous Green-Tao theorem that the primes contain arbitrarily long arithmetic progressions, they got sort of greedy and said, when we're not satisfied with just knowing that you've got one, but we'd like to know roughly how many there are up to n. So how many arithmetic progressions of length k are there up to n as n tends to infinity? What's the asymptotics? And for that, they really needed, the weak inverse theorem that I talked about was not satisfactory. They needed a proper strong one where you would really understand what the structure of these functions f looked like. And formulating the right conjecture to take into account the sort of examples and much more complicated versions of the sort of examples that I just mentioned on the previous slide was already a non-trivial task, which they did in a famous paper of theirs called Linear Equations in the Primes, where they showed that a very wide class of equations, you'd be able to get asymptotics for how frequently they occurred in the primes, if various other conjectures which they formulated could be proved. And over the next few years, they proved all these other conjectures. And in particular, in particular, they had a conjecture that they called the inverse theorem for the uniformity norms, which they proved with Tamar Ziegler, which says, very loosely speaking, that if the UK norm of f is not small, then f correlates with something that you can think of as a generalization of a polynomial phase function. But what exactly that generalization is something that I certainly haven't got time to talk about, involving nil sequences and things like that, from ideas from ergodic theory and lots of things like that. So, but that was a major result, which was the final piece in the jigsaw of this linear equations in primes project. So one, if you're feeling a little bit fussy, you might say, well, actually their proof was, didn't really give bounds, although it might be possible to, if you really worked hard, to extract some sort of bound, but it'd be a very, very weak bound, which sounds a slightly curious thing to say when they're looking for asymptotics for how many times various configurations appear in the primes. But what that's saying is that you don't really have a bound for how long you have to wait until these asymptotics become valid, but they definitely do become valid. So there's no contradiction there between the fact that this result was qualitative, so to speak, but gave interesting quantitative information. So outside the 2018 is doesn't quite make the 5-year cut, but it was a very important result of Freddie Manners to get a new proof of the result that was the first quantitative argument and gave a doubly exponential bound. So not just quantitative, not just something like a tower in a tower of 2 of height or something or other, but actually a reasonable bound. But again, sort of really surprisingly, just this year, James Lang, Ashwin Sar, and Mehtab Sawhney, and Mehtab is, I think, in the audience somewhere, but he's certainly in he's got a quasi-polynomial bound for it. So a quasi-polynomial dependence on of sort of how well you correlate with one of these structures on how large the UK norm is. And also there's a dependence on k as well, obviously. Yeah, so quasi-polynomial just means kind of e to a power of log. So polynomial means e to a linear function in log, and then if you just make that a little bit worse, e to a polynomial in log, it becomes quasi-polynomial. And yeah, so a very interesting application of this is that the bounds for Semiramis' theorem have been lowered for the first time in roughly 25 years. But that's for the higher cases of Semiramis' theorem, so not k equals 3 or 4, but for k beyond 4, they had stood still for a long time. Okay, I must move swiftly on. I think I have So another result that's caused a lot of excitement, I think I'm going to have to say this really quite a lot more quickly than I would ideally like. So let me just give an example to illustrate what this, there's something called the expectation threshold conjecture. I want to say a little example that illustrates what this is about. So in combinatorics and probability and statistical physics and so on, there's a lot of interest in threshold phenomena. So you have some random object and there's a parameter p that says how likely you are to choose certain bits, like that might be a random graph. There's a probability p for each edge of whether you choose it or not. And then you're interested in, as you raise p, when various phenomena start to occur. So let's stick with a random graph case on Hamilton cycle. So Hamilton cycle is a cycle that visits every edge exactly once, sorry, every vertex, I mean, exactly once in the graph. So if I form a random graph with edge probability p, which it's important this depends on the number of vertices, this p, it's a function of n. So I gradually increase p. I want to know at what point does it suddenly become, sorry, I'm giving the game away slightly, say suddenly, at what point does it become more likely than not that the graph will contain a Hamilton cycle? At what probability? And that's called the threshold probability. And one of the reasons it's interesting is that it seems that it's even been proved rigorously that for a very wide range of phenomena, the appearance of these of the phenomena is very sudden. So there will exist some threshold probability. Well, that's defined to be the point at which the probabilities are half. Typically, if you lower the probability very slightly, then the chances of having a Hamilton cycle will be more or less zero. And if you raise the probability, then the chances of having a Hamilton cycle will be very large. So we often see graphs sort of that look like this. So here's the probability of an edge or whatever it is in your structure that you're putting in at random. And then this is the probability that the phenomenon you're interested in occurs. And there'll be some threshold where it sort of jumps very, very sharply. So for Hamilton cycles, it's known that this threshold, Ks, stands for, earlier on there was AKS. Perhaps I forgot to mention that's Aitai, Komnosh, and Semerady. They've proved so many things that in combinatorics we know them as AKS. So I just thought I'd write KS because it was Komnosh and Semerady. So they established that the threshold is round about log n plus log n divided by n for Hamilton cycles. There's a very nice thing called a hitting time result. So trivially, if you've got a Hamilton cycle, then every vertex in the graph has degree at least 2, because it must do to produce. And it turns out that you can prove that with very high probability, or high probability, if you just add edges randomly to a graph, the moment at which it becomes the case that every vertex has degree 2 is also the moment at which you have a Hamilton cycle. And working out what the probability should be to have every vertex of degree 2 is quite a lot easier. So sort of if you're given for free the hitting time result, then you can sort of then establish for yourself that that's a reasonable probability. Okay. Threshold probabilities are typically rather hard things to estimate, but there are other things that are much easier to estimate, which came to be known as expectation thresholds. So for example, with a Hamilton cycle, you could ask not what is the point at which the probability of having a Hamilton cycle is at least a half. So what's the edge probability such that the probability of a Hamilton cycle is at least a half? But you could just ask what's the edge probability at which the expected number of Hamilton cycles is at least a half. So if the probability of having a Hamilton cycle is at least a half, then obviously the expected number of Hamilton cycles must be at least a half, because if you've got one, you've got at least one. On the other hand, the converse is there's absolutely no reason to suppose that the converse to this is true. But some people go a little bit crazy sometimes. And I don't know what's happened there. Oh dear. Technical problem. Let me see if I can understand what's going on there. Looks as though there's been some difficulty with. I have no idea what's going on. I'm going to I'll do this as quickly as I possibly can. Perhaps I'll just try to speak while I'm doing it and just say that there's absolutely no reason to suppose that anything like a converse is true, but if you look at a lot of examples, you see that although the two things are not the same, although the sort of expectation threshold and the actual threshold are not the same, they do seem to be the same up to logarithmic factors. And but just for the examples, these were lots of examples, but the proofs that they were equal up to logarithmic factors were different proofs for each example. You just sort of checked what the threshold was and checked what the expectation threshold was, and now then. Let's see whether Right, let's just see whether there's any better. Oh yeah, that looks better. Okay. Okay. Right. So I hope that doesn't mean I have to sacrifice a problem, but well, actually, okay. So I've oversimplified a little bit, but roughly speaking, the expectation threshold conjecture is a vast generalization of the statement that for all monotone graph properties, the threshold, the actual threshold, should be at most logarithmically worse than the much easier to estimate expectation threshold. And if that was true, it would enable one to at least estimate to within a log factor a lot of different thresholds. And Jeff Kahn may be in the audience. Certainly he's been around this week. So again, I apologize if I'm misrepresenting things, but my understanding is that they couldn't really see how to prove this, and so they did the next best thing, which was just to generalize it out of sight, getting more and more crazy looking statements that they really were pretty skeptical about whether they were true. They're in writing as saying there's no real reason to believe this is true, but we can't seem to disprove it. So here's a quick indication of how you generalize it. So I'll take an increasing family, so that just means if I got a set and I got a superset, then the superset must be also in the family. And I'll choose a random subset of the integers, picking each. So we can think of the set as, for example, the set of all graphs that contain a Hamilton cycle. So if I take a bigger graph than one that contains a Hamilton cycle, the bigger graph also contains a Hamilton cycle, so it's closed upwards. And then the threshold is, I pick my points independently at random with probability p, and then I ask myself, is the set that I get, does it belong to this family? And then the point at which the probability surpasses a half is the threshold for that set, for that family of sets. Now we have this definition, we call the set p small for some probability p between 0 and 1. If you can find some other family, which we think of as a sort of covering the set, the family of sets. So the first property says that every set in the family has a subset. So my first family is F, my second family is G. Every set in F has a subset that belongs to G. And a good example of G to think of here is just the set of minimal elements of F. And in many cases, that would be what you want to take. So for example, if it is the set of graphs that contain a Hamilton cycle, then maybe G will just be the set of Hamilton cycles. And you say it's p small. If that's the case, and then if the sum of overall G of p raised to the power of the size of G is at most a half, and if f is p small, then it's easy to see that the probability that that A belongs to the set system when you choose it randomly is at most a half, because the probability is the probability of this. Probability you can find some G. It's at most the probability you can find a G that's a subset of that, because they covered all the sets. And the probability that you can find some G is at most the sum of the probabilities that G will do the job. And the probability that G will do the job is the probability that G is contained in A, which is exactly this P to the G. So you get sort of trivial inequalities here. So that gives a proof that if you take the sup of all P's such that A is P small, then the probability that the threshold for the family will be at least as big as the sup of P that such that A is P small. And we call that the expectation threshold in a slightly more general context. But as I say, if you sort of specialize to G being minimal elements and whatnot, then it's sort of pretty similar to what I was saying before. And so the full expectation threshold conjecture was that these two were also equal to within log factors. And so this was the famous Kahn-Kallai conjecture. And so there was some, so there's a result that's just outside the 5-year bounds. I might have talked about if we'd had this conference a couple of months ago, but I think because I'm short of time, I'm going to run on. There was a fractional version of it that was proved by Keith Frankston, Jeff Kahn, Bhargav Narayanan, and Jin-Yoon Park, where instead of it's a sort of linear relaxation of the full conjecture, which sort of makes it an easier, or in principle makes it an easier thing. It brings in the potential to use linear programming type ideas. So instead of your G, instead of whether you choose G, a set to belong to G, either it's in there or it's not, it's sort of, you attach a weight between 0 and 1, and instead of saying every element of F must exactly contain an element of G, you want just the sum of the weights of the things in G that are contained in A should be at least 1. So those sorts of relaxations often make problems easier. I definitely don't want to say that it made the problem easy, because this was itself a notorious conjecture, a sort of fractional version, which was, and then so it was a very big breakthrough just under 5 years ago, that the fractional version of the Kahn-Kallai conjecture was true. And then a couple of years ago, Jin-Yoon Park and Hui-Tuan Pham, and Hui is here in the audience, another person is here in the audience. So I feel slightly embarrassed talking about this in front of him, but have now proved the conjecture. It's not a 4-page paper. It's I would say sort of, if you subtract the introduction and the bibliography and things, it works out as about a 4-page proof, which came as a big surprise. There was a potential route to it, which would be to show that the expectation threshold and the fractional expectation threshold agree to within a constant factor, but as far as I know, that's still an open problem. They took a different route to it. Now, actually, although I've got 2 problems to do in 5 minutes, they're a bit quicker to do, I think, and I've less technical and sort of nice, friendly problems to go out on. So the next one, there's a conjecture that many, many people, I've been interested in it for a long time, and I sense that the interest in this conjecture just is going up and up. Everybody seems to be talking about it. Erdős-Heinel conjecture. So going back to Ramsey theory, we can ask, do the bounds for Ramsey's theorem improve a lot if you add the extra condition that your graph does not contain an induced copy of some fixed subgraph? So an induced copy means, well, I'll give the particular example I want to talk about. Say your graph that you're talking about is a pentagon. So you want to say the graph, you can't find 5 vertices in the graph like this such that all these 5 are joined and these 5 are not joined. So that's what we mean by an induced. It's sort of the subgraph induced by those 5 vertices. It's not just that it contains those edges, it contains those edges and doesn't contain those ones. Why might one expect the bounds to improve? It's because, as I mentioned earlier, that the best known lower bounds for Ramsey's theorem come from taking random graphs. And if you take random graphs, then you get copies of whatever you want, just with high probability. The probability of any 5 vertices do this will be 2 to the minus 10. So if n is large, the expected number of induced pentagons will be very far from 0. So when you start to think about it, what seems to be the thing that you could hope to be the case, I don't want to say that it's probably the case, but you certainly could hope to be the case, would be that you actually get a power type bound, n to the delta, where delta would depend on whatever this graph is that you're forbidding to occur as an induced subgraph. And it's been proved for certain simple graphs, and then there are certain operations you can do on graphs, so that if you know the Erdős-Hajnal conjecture is true for this graph and for this graph, then you can sort of put them together, and it must be true for the graph that you put together in various ways, which led to families of graphs for which the conjecture was known, but quite, very restricted families. So for example, well, it's clear actually that if the conjecture is open, it could not be the case that if you pick a random graph, it would never be known for a random type graph, because a random graph would then contain. But anyway, maybe more frustratingly was there were some very simple graphs of which it was not known, and the one that became the sort of most notorious special case of Erdős-Hajnal was in exactly the pentagon. So if you had a graph that did not contain a pentagon, an induced copy of the pentagon, which is sort of had a nice symmetry about it because its complement is also a pentagon. Must you get a power type improvement in Ramsey's theorem? And that's another problem that I've certainly spent quite a lot of time thinking about in the past without success. And that one has fallen 3.5 years ago by those authors. One of the reasons to be interested in that is that there's a whole sort of theme going on with sort of between model theory and combinatorics, where it turns out that if you impose extra conditions on graphs and other structures that are of interest to model theorists, then you can improve bounds for various results very, very substantially. And so the Erdős-Hajnal conjecture sort of has quite a similar flavor to that. And so model theorists are interested in it as well. And there's been quite a nice interplay between model theory and combinatorics over the last few years. But one last result before we finish. This is a notorious open problem in combinatorics called the union-closed conjecture, which is, I've put associated with Frankel. I have heard it said that it was sort of in the air before Frankel actually wrote it down. I'm not quite sure what the history is there of who really conjectured it. So it's a very simple conjecture. You've got a family of sets, let's say a finite family of sets. It's closed under union. So if I have 2 of them and I take their union, that must also belong to the family. Can I find some element that's contained in at least half the sets? And the obvious family to think about is the family of, say, all subsets of 1 to n, where every element will be contained in exactly half the sets. And once you see that example, if you haven't seen the problem before, then if your mind goes along the following sort of, perhaps you could just do some averaging argument and just say on average each element is contained in half the sets. Well, there's a very simple example or class of examples that shows you can't just do it simply like that. So supposing my 3 sets were 0, 1, and 1 up to 100, then those are closed under unions, obviously, but a typical element will not be 1. It will be one of 2 up to 100, and that will only be in one of the sets and not 2 of the sets. Now, if you see that, you sort of see, well, 2 up to 100, they're sort of morally, they're equivalent to each other in this family. So perhaps if we could just find some cleverer measure in which we said, I'll sort of think of 1 as having measure 1/2, and the rest of 2 up to 100 having measure 1 over 198 or whatever it is, then we'd get a suitable averaging argument. And so perhaps we could just find some nice measure depending on the sets, on the family of sets, and then do a nice averaging argument. But you've got to be a little bit careful, because I can give you, if the conjecture is true, then there certainly does exist such a measure, just the point measure at the point that's contained in half the sets. You'd have to sort of impose some kind of non-triviality condition on the measure to make it, you'd have to say there exists a measure with some extra properties for it not to be, I mean, for that to be anything like a kind of strategy of proof, and nobody's managed to do it that way. The best known result until very recently was that you can find some element that's contained in at least, if the family has size n, in n over log n of the sets. And yeah, so 1994, and I'm nearly out of time, but let me just say that another result that hit the headlines within the combinatorial community was the first linear lower bound for this. So the first argument that showed that you can get a constant fraction of the sets, or you can get an element that belongs to a constant fraction of the sets. Well, I was just a little bit of a little bit has happened since then. So yeah, Gilmer got this, Justin Gilmer got the bound of 1 over 100, gave some reasons to suppose that his method would not do better than 3 minus root 5 over 2. Within a very short space of time, so a lot of people came in and started thinking about it, and Will Sawin came up with an argument that sort of in principle ought to get better than 3 minus root 5 over 2, and in the end that's happened, and now actually the record is a little bit better than 3 minus root 5 over 2, so that isn't in fact the barrier, but for this more. But I think the general feeling I get from what I've read online about this is that people don't believe that the current methods can be pushed to prove the whole conjecture without some extra fairly serious new idea. But yes, I've mentioned on the slide that Gilmer used a very, very nice argument using entropy. And I'm definitely out of time now, but I've managed to get through my 6 problems. Just to conclude, I just want to, I think I've basically said this already, but so the first thing, it's extraordinary the rate at which these really famous problems are being solved. And the fact that they're being solved, a lot of them are being solved by very young people, is sort of nice for someone who's my age. And thank you very much.